Hello students, in this video we'll discuss covariant differentiation of tensors of any order. Let's recall that if AI is a contravariant tensor, clearly of order 1, right? Then this operation over here, the jth covariant derivative of AI, defined to be partial AI partial xj plus gamma ij l al is a mixed 1-1 tensor called the covariant derivative. We've proven in a previous video that this actually has a tensorial property, tensorial transformation law, called the covariant derivative. Okay, excellent. And now, how would I use this to define, how do I define the covariant derivative of a covariant vector? So if bi was a covariant tensor, clearly of order 1, then gradient j bi, which is partial bi partial xj minus gamma ij l bl is now a 2 covariant tensor. The same proof that we did in the previous video will work for this argument as well. So in other words, if I covariantly differentiate a covariant vector, I'm going to arrive at another 1-up covariance. Then there comes the issue that, well, you've defined covariant derivative. How do you do contravariant derivative? Contravariant differentiation is not any different, so contravariant differentiation is obtained just by raising the index, right? So in other words, if I look at this operator over here, I'm going to say that gamma contravariant differentiation k is really just GKL of covariant differentiation, right? So you just raise the index, right? So it suffices to talk about covariant differentiation, and then otherwise I'll just raise the index over here. Okay, excellent. So now what I'd like to do is I'd like to figure out how to do differentiation in the second order. We'll see how that will generalize in higher order things, right? So second order tensors. Okay. So let's look at this one first. How would I do the covariant derivative of a two contravariant tensor bjk? If this was a 2 contravariant tensor. What would this be? Well, it always has this form over here, partial bjk partial xi, and then I'll have 2 terms over here, 2 contravariant terms. So I'm going to have a gamma, and I'll have an I in the bottom, an L on the L down here. Then I'll have a J up here. Then I'll have a BLK, something over L, plus gamma of I and a dummy index. Just to show the dummy, I'm going to call this index M over here. Then a BJM. And what am I missing over here? I'm missing the K index, so the K index goes over here. So now I have something over K. That would be how you do a covariant derivative of a 2 contravariant tensor. If you want to do a covariant derivative of a mixed tensor, JK, what will you get? Well, you get partial BJK, partial XI. Then the contravariant term we get a plus gamma I. So the contravariant term is going to be an I, and that stays put. And then the K is going to go to the bottom, and then I have to sum against J. So I'm going to put an L over here for the dummy index. And then we're going to have a what? Then we're going to have a BL, and then a lower K. Okay? And the J goes on top over here for the gamma, like that. Excellent. And then we have a minus what? Then we have a minus gamma. I need an I in the bottom. I need a K in the bottom, because we're going to sum over the bottom index now. A K in the bottom, and then we're going to need a what? We're going to need a J on top, And we're going to need a what? I need a dummy index on top now. So I need a dummy index m. We'll have a bj. And then we'll have a m down over here, right? So now this still has the form of what? It still has an I lower, a k lower, a j upper, right? Over here I have a j upper, an I lower, and a k lower. So I have exactly the right form. If I wanted to do a covariant derivative over here, I of b, and then let's say jk, so two contravariant covariant terms, you'd have partial b jk, partial xi, then minus gamma I. And since we're on the bottom index over here, I'm going to substitute one of the j's, j, and then L for dummy index, b, L, k. And then minus gamma, I need an I and a k now, an I and a k, dummy index m, b, and then I need the j to stay put, because I have three things in the bottom, and then an m down over here, like that. Now, of course, if there's symmetry in these tensors, I can sort of combine some of these things into more useful form. But now you can sort of see the general principle. They have to covariant differentiation adds one covariant component to the differentiation process. So if you have a tensor of order m times n, where m is the covariant and n is the contravariant, if you do a covariant derivative of that, you'll have an m plus 1 n. So it's basically raising the order of the tensor in one covariant direction. Likewise, doing contravariant differentiation will raise the order of the tensor in one contravariant direction. Okay, excellent. So let's do an example of this. This is an example of something that will come up later on. So here's an example of using this contravariant differentiation. Let's find the covariant derivative of delta, and let's say jk like this, where that's just the Kronecker symbol. So delta jk is the Kronecker mixed tensor. All right, so let's do it. So definition, so solution. Delta kj is going to be what? Is going to be the derivative of delta kj with respect to xi. And then we're going to have let's do the covariant derivative first over here. So we're going to have a plus gamma of ik. And then we're going to, I want to change that k actually. So that's k is going to stay in the bottom of the delta. So we're going to change that actually. Let's change that. It's going to be a gamma of I. If we're doing the contravariant term first, I'm going to put an m down over here. Then I'm going to put a what up here? I'm going to put an m up here, and then a j up here, and then a k down here, like that. And then we're going to minus gamma of what? The I and the k stay downstairs now. So we're going to sum over so actually the I and the k have to stay put, so I'm going to put a k down over here, right? So we're going to sum over the bottom guy. So we'll have a what on top, a dummy index m on top, then we'll have an I and a k in the bottom, then we'll have a delta j over here, that stays constant, the contravariant term stays constant, and then down over here we're going to have the m. So that will be that's the covariant derivative of this Dirac or this Kronecker function over here. Now what is this going to be? This term over here is going to be 0 because the Kronecker function is either 0 or 1. So when you differentiate it, it's a constant in either case, the derivative is 0. Then over here, what are we going to do? We're going to place k and m with each other, right? So this first term over here is going to be a plus gamma of I k j, and this term over here is going to be minus, now I replace j with m over here, so it's going to be minus gamma of j I k, and lo and behold, those terms cancel out, and we see this is equal to 0. Now that might not seem like something that's terribly interesting, but that the derivative of this Kronecker tensor is going to be 0 because we know it's basically either 0 or 1, depending on the indices, so its derivative should be 0, right? But another really interesting property we're going to prove in a further video is that you do the same trick over here. If I did the covariant derivative with respect to k of the metric tensor, we're going to see in further videos that this will also give us 0, right? So it's a property that we want to figure out the properties of when a covariant derivative is equal to 0 gives us really valuable information about sort of the geometry, the underlying curvature properties of the manifold or the curvature properties of the surface that we're on. And so understanding how this covariant differentiation works and higher order covariant differentiation is going to be very useful for us in coordinate change, understanding curvature and different sorts of applications of flows along manifolds. Thank you very much.